how can we interpret maximum likelihood estimation if our model is incorrect? Say, if our observations don't really come from a Poisson distribution, but we nevertheless apply Poisson MLE. To give this an interpretation, we're going to have to think about models as approximations rather than reality. And in this video, we're going to talk about a way of determining how well a particular parametric model approximates some true unknown data generating process. The way we're going to measure this is called the Kullback-Leibler divergence. We'll use the notation f of y theta to denote our parametric model. So theta is the unknown parameter vector, and y is some random vector. And we will use the notation p naught of y to denote the true unknown density, or PMF, depending on whether this is a continuous or a discrete random vector. We define the Kullback-Leibler divergence from p naught to the parametric model f theta, denoted KL of p naught semicolon f theta, as follows. It's the expectation of the logarithm of the ratio of p naught of y, so this is the true unknown density, to the model f y theta. And here what we have to bear in mind is that p naught of y is some function of y. F of y semicolon theta is another function of y. So we're taking some kind of expectation of a function. The function happens to be complicated, but it's still a function of y. We'll unpack this and start to make sense of it in a few steps. First, notice that because the log of a ratio is equal to the difference of the logs, we can rewrite the Kullback-Leibler divergence as a difference of two expectations. The first is the expectation of the log of p naught of y, and the second is the expectation of the log of f of y. There's a special name for this second term. We call it the expected log likelihood. It's important to be clear about exactly what these two expectations mean. To help us understand, it's useful to write them as integrals. Let's take each in turn. The first one, the expected value of the log of p naught of y, is the integral of the log of p naught of y multiplied by p naught of y dy. In other words, this is an expectation of a function of y where we're integrating against the true distribution of y. And the same thing goes for the other expectation. So the expectation of the log of f of y is defined as the integral of the log of f of y multiplied by p naught of y. So each of these expectations is an expectation of a function y where we use the true distribution of y to calculate the expectation. If at any stage you get confused, you can always write these expectations as integrals. Just remember that we are integrating against the true distribution, not our model. And now that we know what these expectations represent, we can see that in fact the first of the two, namely the expectation of log of p naught of y, in no way involves our model f and in no way involves the parameter theta. It's an integral that purely has to do with the true distribution, p naught. So for that reason, this first term in the Kullback-Leibler divergence is actually a constant as far as any model that we might want to write down is concerned. That's going to turn out to be very important later. The Kullback-Leibler divergence has a number of important properties, and here are the three most important ones. First, it is asymmetric. If you switch the order of p naught and f theta in this KL, you're not going to get the same thing. And that should be pretty clear if we take a look at the integrals on the right-hand side of the slide. You can't just interchange f and p and get the same thing because you're going to have totally different integrals. Second, and this is a property we'll come back to on the next slide, the Kullback-Leibler divergence cannot be negative. It's either positive or zero. And it's zero if and only if this parametric model f of theta is the true data generating process p naught. Finally, if we minimize the Kullback-Leibler divergence, that's exactly the same thing as maximizing the expected log likelihood. Now, why is that? A moment ago, I told you that the first term in this alternative expression for the Kullback-Leibler divergence is a constant as far as our model is concerned. It doesn't know anything about f, it doesn't know anything about theta. What that means is, if we were trying to, let's say, choose theta to make the Kullback-Leibler divergence as small as possible, if we were trying to pick the value of theta such that under our parametric model, we did the best possible job of approximating the true distribution using f, then we would discover that that first term plays no role in the optimization. As a consequence, we can just ignore it and state that minimizing the Kullback-Leibler divergence is exactly the same thing as maximizing the expected log likelihood. And that's why it turns out that there's an intimate relationship between the Kullback-Leibler divergence as a way of measuring the quality of a model's approximation and maximum likelihood estimation. There's one last technical detail that we have to be careful about when we're working with the Kullback-Leibler divergence. It can't be negative, but it can be infinite. Now, when would it be infinite? Well, there's only one case in which the Kullback-Leibler divergence can be infinite, and that's if our model, f, rules out some values of y that could actually happen in reality. In other words, if the true distribution, this p0, has a support set, and some, at least one, let's say, of the points in that support set does not fall within the support set of our parametric model, then what's going to happen? Well, when we try to take the integral, we need to evaluate it at any point where p0 of y is not 0. So if there's a point where p0 of y is not 0, but in fact f of y is 0, what are we doing? We're trying to take the log of 0, and that is generally not a good idea. So we just have to be careful that when we define the Kullback-Leibler divergence, in order for it to be a useful measure, in order for it to actually give us a way of telling whether one approximation is better than another, it needs to be finite. So we're going to assume throughout that the support set of our model does not rule out points that are actually in the support set of y. And this is pretty easy to do. If we're working with count data, then we just need to make sure that f allows 0, 1, 2, 3, any possible value that a count could take on. On this slide, we're going to prove the second property of the Kullback-Leibler divergence from the previous slide, namely that it is always greater than or equal to 0, and precisely equal to 0 if the model is correct. To do this, we're going to use Jensen's inequality, which I hope is familiar to you from your introductory lectures on probability. Jensen's inequality states that if phi is a convex function, then phi of the expectation of some random variable y is less than or equal to the expectation of phi of y, with equality, in other words, the two are exactly equal, if and only if either phi is a linear function or y is actually a constant, so it's not random at all. We're going to use this result along with the fact that log is a concave function. So since log is concave, negative log is convex. And I have slightly simplified the notation on this slide. I've suppressed the theta, and I've just written a scalar y rather than a vector, but that's just so that it's easier to read. If you want to see it with all the notation, take a look at the lecture notes. All right, so we're going to try to calculate the Kullback-Leibler divergence. That's defined as the expectation of the log of the ratio of p0 to f. Now, we'd like to write that in terms of minus log. So to do that, we have to exchange the numerator and the denominator of the fraction to make them equal. Now we've got what we're after, which is a convex function. So we've got the expectation of some convex function of some complicated random variable. Now the key here is to realize that the thing that's playing the role of the random variable is the whole ratio f of y over p0 of y. In other words, if y is a random variable, then any function of it, no matter how complicated we want that function to be, is also a random variable. So it's this whole thing that we're treating as the random variable inside of Jensen's inequality. Applying the inequality, we exchange the function and the expectation, and then we add the appropriate inequality sign. So the function of the expectation is less than or equal to the expectation of the function. Now, let's take a closer look at the expectation that's inside this logarithm. If you remember from the last slide, we could write that expectation as an integral when we're dealing with a continuous random variable. So let's do that. And again, the integral uses the true distribution P0 for integration. So we have our function here, f of y over P0 of y. We're calculating its expectation using the true density P0, which we write as the following integral. And now notice that the P0 in the numerator and the denominator cancel. So what are we left with? We integrate f of y from minus infinity to infinity. But what is f of y? Well, this is our model, and the model that we've written down is a density. It might not be the true one, but it's some kind of density, and that means it's going to integrate to 1. So we have -1 times the log of 1, and that is equal to 0, which shows what? It shows that the Kullback-Leibler divergence is greater than or equal to 0, exactly as we set out to show. Now there's one remaining piece, and that's the piece about this equality. So how do we know that when f really is the true distribution, that the Kullback-Leibler divergence is exactly equal to 0? Well, if we take a closer look at this expression, if f is exactly the same thing as P0, then from the very start, we would end up with a ratio of 1. We would have P0 of y over P0 of y, which is 1. So we would be in the case where the random variable to which we're applying Jensen's inequality is a constant. Therefore, if indeed our model is correct, the Kullback-Leibler divergence is exactly equal to 0. This has all been rather abstract, so let's look at an example. Suppose that the true distribution P0 is P0 of 0 equals 2/5, P0 of 1 equals 1/5, and P0 of 2 equals 2/5. This is the probability mass function of a discrete random variable that only takes on either 0, 1, or 2. Now, suppose that we don't know that that's the true distribution, and we instead try to fit a Poisson model. So we can tell that this model is misspecified. The reason we can tell that is because a Poisson random variable can take on any value from 0, 1, 2, 3, up as high as you'd like to go. But in fact, this PMF P0 gives no probability to values that are greater than 2. So we're sure that P0 is not a Poisson distribution. Let's calculate the Kullback-Leibler divergence for this example. To do that, we're going to calculate each of the two expectations that appear in the alternative expression for the Kullback-Leibler divergence that we saw a few slides back. First, we'll take a look at the expectation of the log of P0 of y. By definition, the expectation of a function for a discrete random variable is the sum over all possible realizations of the function of that random variable multiplied by the PMF. And again, notice that we use the true distribution when calculating these expectations. We're using P0. So let's plug in all the possible values of y, all the realizations that we can actually observe, 0, 1, and 2. This gives us the log of 2/5 multiplied by the probability, 2/5, plus the log of 1/5 multiplied by the probability, 1/5, plus the log of 2/5 multiplied by 2/5. Now, what is that? Well, it's a little bit bigger than 1. I don't know out to how many decimals that's accurate, but the most important thing to realize is that it is constant. It does not in any way involve theta, the parameter of the Poisson distribution that we mistakenly assumed that y actually follows. So just to clarify some of the general points that I made on the previous slides, we've actually calculated this first term in an example. We've actually calculated the expectation of the log of p naught of y, and we saw that it is really a constant. Now let's turn our attention to the second term. This is the expected log likelihood, namely the expectation of the log of f of y. That's our model, and that does involve theta. Once again, the expectation of a function of a discrete random variable is equal to that function, evaluated at y, multiplied by the associated probability of y taking on that value, summed up over the support set of y. Again, these expectations are all evaluated using the true distribution p naught. So we're summing over the true support set of y, not the support of a Poisson, which is our incorrect model, but the support set 0, 1, 2. And we are using p naught to calculate the probabilities that go into this expectation. So we have the log of f. Now what is f? F is our model, and that is a Poisson distribution. So f of y is e to the minus theta times theta to the y divided by y factorial. Substituting in y equals 0, we obtain the log of e to the minus theta multiplied by p naught of 0, which is 2/5. Substituting in y equals 1, we obtain the log of e to the minus theta times theta multiplied by p naught of 1, which is 1/5. And substituting in y equals 2, we obtain the log of e to the minus theta times theta squared over 2, multiplied by the probability that y equals 2, and that is 2/5. So simplifying this, combining terms, what do we obtain? Well, I can factor out a minus here, and I obtain a theta minus log of theta plus log of 2 multiplied by 2/5. All right, now notice that this does involve log of 2 times 2/5, but that is just a constant with respect to theta. And since the Kullback-Leibler divergence is the difference of these two terms, the expectation of the log of p naught minus the expected log likelihood, we see that it is equal to theta minus log of theta plus a constant. And that constant is a combination of the constant we obtained in our first calculation and the one that we obtained in our second. But because it doesn't involve theta in any way, we can actually just ignore it. So now that we've seen a calculation of the Kullback-Leibler divergence, let's do something more interesting. We know the Poisson model is wrong, but we might be interested in knowing what value of theta makes the Poisson model as good as possible. In other words, for which value of theta do we make the Kullback-Leibler divergence from the truth to our model as small as it can possibly be? This value of theta, which we're going to call theta naught, is called the pseudo-true parameter value. This is to underscore the fact that it might not be the truth because our model isn't actually what gave rise to the data, but it's the best that we can possibly do given what the true distribution of y actually is. So if we use the result from the previous slide where we calculated the Kullback-Leibler divergence, we saw that it was theta minus log of theta plus a somewhat complicated constant. If we take the first order condition, we discover that the optimal choice for theta is 1. So, by calculating the Kullback-Leibler divergence, which took us quite a while, we were able to work out the pseudo-true parameter value. Theta is equal to 1. The best possible Poisson distribution for approximating this true but unknown to us distribution of y, p naught of 0 is equal to p naught of 2 is 2/5, and p naught of 1 is 1/5, is theta equals to 1. Now, you may be wondering about the relevance of this calculation because in order to carry it out, it seems like I had to know what the true distribution was. And it wouldn't be very helpful if I could give you a way to find out the best Poisson distribution for approximating this unknown p naught if answering the question required you to know p naught. But fortunately, it doesn't. And to see why, let's redo this exercise using a more direct approach. So we already saw that maximizing the expected log likelihood is the same exact thing as minimizing the Kullback-Leibler divergence. So let's run with that. Let's just go straight to the expected log likelihood and maximize it. So if we substitute in the Poisson model, as you may recall from the video about Poisson maximum likelihood estimation, the log of that probability mass function is minus theta plus y times log of theta minus the logarithm of y factorial. So we would like to maximize this expectation. So let's calculate the expectation first. Minus theta is a constant, so we can pull that out. Log theta is also a constant, so we can pull that out. So now we've got an expectation of y. And then we've got a minus expectation of log of y factorial. So again, these constants were pulled out of the expectations. They are non-random. All right, now we can solve our optimization problem. So let's ask ourselves about a different kind of constant. Which bits and pieces are constants with respect to the optimization problem? Well, the expectation of the log of y factorial does not involve theta. So we can just ignore that, and we can focus on the remaining terms. If we differentiate minus theta with respect to theta, we get minus 1. And if we differentiate the expectation of y times log of theta, well, the expectation of y does not involve theta. That's just some constant. So we're just differentiating the log of theta. We get 1 over theta. And that leaves us with the following first order condition. Minus 1 plus the expectation of y over theta equals 0. Rearranging, the theta that solves this problem is the expectation of y. So where does this leave us? Well, we have calculated the Kullback-Leibler divergence in this particular example, and we've found that the value of theta that minimizes the Kullback-Leibler divergence is 1. That's the pseudo-true parameter. But that first approach required us to actually know this distribution p naught, which in practice we're not going to know. We then used a second approach. The second approach, in fact, did not use knowledge of p naught anywhere. If you go back to the calculation on the previous slide, it never entered at any stage. There we found that the best choice of theta was to set theta naught equal to the expectation of y. So do these two methods agree? It looks like maybe they don't. Well, actually, they do. And the reason is, under this particular p naught that I made up as an example, the expectation of y really is 1. So the two approaches coincide, but the nice thing about the second approach, which you might call the direct approach because it went straight to the likelihood, straight to the expected log likelihood, I should say, and maximized that rather than bothering about that constant that's irrelevant in the Kullback-Leibler divergence. Well, this approach, it's general. It works for any true distribution at all. So what we see here is we don't actually need to know what the true distribution is to determine which value of theta does the best job of approximating it. So the pseudo-true distribution in general, if you fit a Poisson model, but the truth could be anything, possibly not a Poisson, is to set theta equal to the expectation of y. And that makes sense because we know that for a Poisson distribution, theta is the mean. So this turns out to be the same thing as matching moments in this particular case.